So in the last video, we reviewed what the map was and our simple implementations from the beginning of the quarter: array map and linked map. And one of the things that we talked about was in these implementations, the thing that really slowed it down in the worst case, the case where we ended up having to look for a key that ended up being at the end of the implementation, was this scan. The fact that we had to start at the beginning and loop till the end to find the key we want. And so the question here is these put, get, and remove has some big theta of n runtimes, and they come from that scan operation. So could we, instead of trying to scan for the key, use some big theta of 1 operation to improve the runtime in total? So can we replace that linear runtime with a constant runtime? And one such possible constant runtime operation that we might find useful here is this idea of array indexing. So whenever you access a value in an array, so you say, here, I have index I want to access data of I, or you want to set a value at a particular index, we're going to consider that to be constant runtime. It's a simple step that the computer knows how to do instantaneously. Now, what if for any particular key, we know exactly which index in the array it's referring to? So we're going to be thinking about array implementations here, not linked ones. So what if I could say, here's the key for CSE 373. We know that belongs exactly in index 7 or something. So we want some way of saying we know exactly where each key belongs. Now, one way to go about this is, what if we restrict the keys to only allow integer keys? So we'll only allow the keys to be numbers between 0 and some large maximum number. This is simplification for now. We'll talk about in the next video how to generalize this to work for any type of key, strings or whatever else you want. So this is going to be kind of our motivation for this first kind of fancier implementation called DirectAccessMap. Now let me remind you, for your project, you're only implementing array map and that last one, separate chaining hash map. These two in the middle are kind of stepping stones to get us to all the ideas in separate chaining hash map. So we're not going to implement these directly, these middle two. So here's the idea of DirectAccessMap. We want to use an array that's going to store our key value pairs, essentially. And since we're going to restrict our keys to only be integers, our idea is we'll use the index of that key to store the value. So for example, if you're going to put the key 3 with the value Alex, we can store Alex at index 3. Because again, we're simplifying our structure right now that only allow integer keys. So put, you just put it at the index. To get, you just go to the index, say data of 3, and you get Alex back. So this is essentially, this implementation of DirectAccessMap is essentially just an array that could store any type of values, because we're just using the key integers as the index, essentially. So put, get, contains key, remove, we can implement those all by just going to the index for the particular key. So this is how you might implement this in code. We're going to assume that we have a field called array that's going to store all of our values. It's going to have a spot for every possible key that we're considering. And so if you're going to put something there, you just go to the key index and then you set the value there. Contains is just making sure that there's something there, that it's not null. Get is just going to that index and returning whatever value's there. And remove is setting whatever value there is to null. So it's really just using this big array to store values at the index for whatever the key is. Because again, we're restricting keys for a second to only be integers. So I want you to try is, well, actually, sorry, before you try something, one thing to recognize, or I hope that you'll be able to see here, is that no matter what case, no matter what key you're looking for, or what key you're accessing or removing, all of these operations, no matter the best case or the worst case, are all going to be big theta of 1. They're all going to be constant time. And the reason for that is the only operations we do here are array accesses, which we just said were constant time. So hopefully I can convince you here that all of these operations will be constant time. What I want you to try is to articulate, what do you think the pros and cons of using a data structure in this way might be? So item pool now supports 3 response questions, so you can write out a couple sentences here. What's a benefit of using this direct access map over our array map? And what's a potential drawback? Take a second and try to answer that. Whoops. Okay. So there are one pro that we just highlighted was that everything was super fast. Everything was constant time, which is exactly right. Unfortunately, there are a couple cons here. The first is, in order for this to work, we're going to have a spot in our array for every possible integer key. So if we want to store keys between 0 and 999999999, that is going to be a really big array that we're going to have to store in memory. So that would waste all of the space between all the values in our data structure because we're going to need to have a spot for every possible key. This is kind of like if you want to have a bookshelf and you want kind of fast access to any book, you made a bookshelf that can hold every possible book that was ever written to fill in the couple Harry Potter books you might have. That's one downside that I identified. There's probably others. Another downside I identified that we're not going to solve right now, but is one that we could point out, is right now, due to this restriction, we can only store integer keys. So it's not going to be the case that we can make some kind of fancy map that has strings as keys. But the fact that these integer keys are there is what's making this structure useful or fast, is we're able to quickly go from key to array index. You might even call that the key idea here, because that is the thing that allows us instant access. We know exactly which index to go to because there's a one-to-one mapping from key to index. So with that idea, maybe we can try to figure out how we could fix that first con of a little too much space. So our current idea is to create a giant array with every possible integer as an index. Now, the problems here is we probably can't actually make an array that big. Your computer will probably run out of memory. And it's super wasteful because if you're only going to have a couple values in your dictionary, then why use all that space in the world? So our second idea is to create a smaller array. Now, if we're going to make this array smaller, there's not going to be an index for every possible key. So now we're going to need some kind of translation from the integer keys that the client is going to be thinking about, 504, 1, and 9002. And we need to somehow translate that to an internal index that we can then quickly access. Now, there are, the pretty clear problem here, though, is how would I come up with such a translation? How can I make a translation that works for any possible integer key to take me to an index? So this is where we enter the idea of a hash function. So we're going to call a hash function essentially any function that takes data from an arbitrary size down to a fixed size. What we mean by that is, in our keys that we're letting the client consider is any possible number, any number that they would want. Our hash function's job is to take that gigantic set of possible numbers and make a function that takes each one down to a small set of numbers. So maybe the numbers between 0 and 9, if our array is only 10 long. So this hash function is supposed to reduce the size of the numbers we have to consider in some sense. So we want this translation from these integers to valid indices. So one simple approach to do this is to take the key and mod it with a little percent sign by the size of the array. So for example, 9002 mod 10 is 2. So we can maybe say stored at index 2. So as a quick refresher on mod, mod is a remainder operator. So just like you could take 3 divided by 2 and get 1 if we're thinking about integer division, 3 mod 2 would be 1 as well because there's 1 left over. So I have some examples here. 14 mod 4 is 2. And the reason is when you do 14 divided by 4, we have 2 left over from that remainder because 4 goes into 14 3 times mostly, and then there's some leftover stuff, 2 left over. So this mod operator is a leftover thing. Now, mod has a lot of applications in computer science. One is you can always use it to obtain digits of a number. If you mod something by 10, you can grab its last digit, which is pretty useful. You can also use it to figure out its parity, whether it's even or odd. So if you mod a number by 2, if that value is 1, it means it was odd, otherwise it's even. And the most useful context that we're going to use here is it's really useful for limiting numbers to a specific range. So if you mod any number by 12, in my last example here, any number modded by 12 will result in a number between 0 and 11, both of those inclusive. So it's a nice way of taking this large range of values and squishing it down to a smaller range. And so this idea is why we're going to use mod for our hash function here. So here is going to be our SimpleHashMap implementation. So what we're going to do is we're going to take each key, integer key, and mod it by the length of our array to find a valid index. What this means now is we can now store a smaller array. We can now only store an array of size 10, and it would still work with any key. Again, only integer keys right now. We're going to still assume they're integers. So if you put 0 with the key, the key 0 with the value I, well, we start by modding that key 0 by 10 to get 0, and we're going to store it in index 0. Then when we try putting 8 with maps, well, 8 mod 10 is going to be 8, so we're going to put the value maps in index 8. Straightforward so far. It gets a little bit more interesting once we get to larger numbers. So now when you want to put 11 with the string, the heart symbol, you first use our hash function, mod by 10. 11 mod 10 is 1, because that's the remainder when you divide, which says we're going to put this heart symbol in index 1. And similarly with when we put 23 in hash, it's going to go to index 3, because we mod 23 by 10 to get 3. So that's going to be our big idea for the SimpleHash function. Now, the way we'd implement this in code is it's very similar to our last array implementation, the DirectAccessMap. The only difference now is instead of just going to index key, we need to call this helper function hash2validIndex, which is just going to mod the key by the length of the array. And it's always going to guarantee it's going to be a number between 0 and the end of the array. So I want you to take a second. You probably might already start seeing that this could potentially cause some problems. Is there an input that I can pass to a put call or a get call that would cause a problem? Take a second and try that out. Okay, so is there a key that we could put in here that would cause a problem? I think there are actually a couple, but one I would argue is what if you use the key 20? So what if I say put 20 with we? Well, what would we do? The first thing we do for a put call is we start by calling hash to valid index. What's the valid index for 20? Well, 20 mod 10, 10 divides 20 evenly, so the leftover is 0, which means we're going to try to put it in index 0. But if we put it in index 0, well, there's already something there. And so the place where we belongs with key 20 is going to be the same place where I belongs with key 0. What we have just called, or what created it, is what we call a collision. And collisions can happen with these hash functions because kind of by definition, because I was saying take this large set of possible keys, every possible number, and translate and make a translation that only goes to a small set of possible values. If we're taking every possible number and trying to map it to a number between 0 and 9, we're going to run out of spaces. We're going to hit a collision where two things have to map to the same value. And so this collision is going to motivate our next and final implementation of the map ADT, which is going to be called our separate chaining hash map. And we'll introduce that and how to handle non-integer keys in our next video.